Okay, so here's the last part of our series for this I guess series of problems. Now we're showing if you remember, actually let me just go to it here. Part C. We were doing the transfer function under closed loop feedback control, and then we had a sinusoidal uh transfer function multiplied by input of his, well, I'm sorry, a closed loop, I'm sorry, open loop transfer function times the input of a sinusoidal input, well, just a sine going inside, and we had a phase coming out. Well, that was our feedback. So I think last time I was saying how I left the expansion of that uh, partial fraction decomposition to the next part, which is right here. Trying to find it right here. So essentially, it's that part in yellow. I don't know if you can see cursor here. So that part right there. Um, Mainly focusing on how these expansions come about here. So I'll go ahead and rewrite that. But I guess kind of to just show the general form. You remember I had this right here. It's basically a very big polynomial. So for however many m terms and n terms for the denominator, you have coefficients b and a, and the denominator of that polynomial in the, well, the polynomial in the denominator, I should say, is what's getting expanded out in that partial fraction decomposition, so that we can do the inverse Laplace transform. So what we're looking at today is how those expansions come about. So those roots are, I guess we call them poles. Um, they can exist as either real or complex. And since we're assuming there's coefficients that are real in the polynomial of the denominator of the transfer function, if those are real, which they are, then you can have real roots. But if you have complex roots, then those complex roots must exist, as the problem states, as conjugate residues and poles. So you have coefficients that can be essentially, well, let me just write this out. So we have our transfer function. I'll just say this overall. So that's, well, open loop technically. So you would normally break that down. Well, let's just show what it was earlier in that other frame. I think we had a to the m or something. Or I'm sorry, the mth term of a with s to the m plus, and then you can do m minus 1, and that's s to the power. And then you go all the way down until you're at, I don't know, a0 or a1. The same thing can happen for the denominator here, so we'll use n, so s to the nth power, and the process repeats. I don't know why I drew a m, so it should be bn sn minus 1, so this is also minus 1 plus, and then I should show that there's more in between, so a0 maybe and b0. So you can imagine for however many m and n turns, usually, well, the case is that the denominator has a higher power than the numerator. And that's because we don't want transfer functions can't predict the future. So that's the case with that. Yeah, so this gets broken down after we do partial fraction decomposition. Those roots of this denominator polynomial get broken down into what we saw earlier, these a1 terms over s plus b. And we know that this corresponds to, I'll do 2, just to get the example across here. So a2, s plus b2, so on and so forth. And we know that this was the inverse Laplace of an exponential function. So this would be the inverse Laplace, something like this, a1 s plus b. I'm sorry, did that the other way around. So it would be the Laplace of that exponential, if it was a1 e to the negative b1t, would net us exactly what we have in our partial fraction decomposition. I'm a little far away from my mic, so hopefully you can hear me well. So that's what it looks like after it's decomposed. And also you can notice that the more traditional form of writing this, I know in class we've been using s plus b1 since that's what Carlos has been telling us, but we have a1, usually it's written as s minus the p1. So this is known as the p1 is the poles, and the coefficients up top are known as residues. So I can show that really quick. In a collab, there's something called sci-pi signal residue. Let's see here, like so. Actually, it might help to do a split. So we're gonna do, we can write a polynomial actually. So let's do that. So do something pretty close there. So if we have a polynomial plugging in numbers to the general form we had earlier, maybe 4s cubed plus 3s squared, and then we can skip some s's and then go all the way to the last, which is just the last term, which is just a value, or a constant, I should say, so like 0.1. And then as I said, the denominator is higher order, so we can go maybe 6s to the fourth. Maybe skip one and then go to 5s cubed, skip another and go s, and then maybe 0.7. So I'm making these numbers up, but this is what a transfer function could look like. So maybe experimentally determined or whatever. So I'm here in our collab, and then using this sci-pi signal residue, it actually does that partial fraction decomposition. Notice that we didn't do these by hand on the right-hand side there. Well, that's a fraction I made up, but normally we just do this computationally. So this is what it would take the form of. Remember, that's kind of what I drew earlier, that general form of that transfer function. And then what this residue does, it's a function that takes b and a. So let's see what those are arrays of just coefficients. And you notice that b is the numerator, a is the denominator. And it looks like, just looking at this, so b, the higher power is the value that comes first, and it descends in power, as you can see with the m minus 1. And it exactly follows what I drew earlier. So we'll go ahead and do that. Just kind of looking across here. Let's see, get a little closer. So I have some values up top there just to compare if this made up value doesn't give me the things I'm looking for. Namely, I'm looking for a conjugate pair to show off what it does look like and why those exist. So if I have an array, I should have numpy imported at the top already. So remember, b was the numerator, so I go 4, that's the highest power, then 3, so then we skip s, so we put a 0, and then we have 0.1. I'll go ahead and copy that for the A array. And here we start with a 6 as the fourth, 5s cubed, so 5s cubed, we skip squared, and we have s as 1, and then we have a 0.7, 0.7. And now I think I have it imported already. So residue takes b and a as the arguments parameters, and now we have our outputted fraction decomposition. So I'll go ahead and in. So let's see. It doesn't look like there's quite a oh, this actually might be a conjugate right here. So this happened earlier where it's not stacked side by side, which is preferred, but essentially we're looking at these two pairs here. You'll notice that these are, well, all of these are complex numbers, but the conjugate pairs are the ones where the sign is flipped between the real and the imaginary. So this is 0.19 plus 2.7. That's the imaginary portion. And then this is 0.19 minus that 2.7. So that's exactly what we're looking for. They exist as pairs because, well, if we have real coefficients in the denominator polynomial of the transfer function, they exist as pairs so that the imaginary portions cancel out. And I can show that as well. I had some earlier examples. I think this is the one from class where it actually stacked up really nice side by side. But I mean, the point is that if they show up as pairs, so I think this is another one here. So, I mean, that's all the coding. I mean, technically we don't even have to do this. So just to show an example, and then we can go right back to our derivations here. This up, keyboard back, and then now I think it's pretty much all derivation from here. So I said we would show how those conjugate pairs cancel out the imaginary portions. But there's also, just to notice or preface, I will also be talking about the real roots, not just the complex roots. So part one's asking about the complex roots, and we'll also derive that time domain response at sinusoidal, exactly the same as the phase shift we saw with the sinusoidal after it went through our open loop transfer function. So we'll see that derived as well. So we'll do that right after I show how those imaginary portions get canceled out, which is just some algebra here. I'll do it kind of explicitly so I don't make mistakes. So yeah, if we had the conjugate pairs, remember they exist as, well, pairs. So we had maybe something like C minus, what did we do? C plus DJ over S plus A plus BJ. And then we have C minus DJ, S plus A minus BJ. So you'll notice that it's not quite the same, I don't know, form that we showed earlier. So in this case, instead of just real values, now we have complex values or complex numbers for both the residues. So residues are the coefficients on the numerator, and the poles or the roots in the denominator. So now we're introducing that imaginary portion there. So to simplify this, well, it's a partial fraction decomposition. So we're going to multiply across the denominators. So we'll might take a bit. So we have CS at the top. So CS. So I'll do this times this, and then eventually this times that. So we have, let's do this quickly here. So CS, then C times A, so CA, and then C times minus BJ, so that's minus CBJ. And then we do the DJ term, so DJS, I'll do parentheses here, DJS plus A DJ, and then we have DJ times negative BJ, so J squared, remember J is square root negative 1, so if we get J squared, that's just negative 1, so instead of a negative, it's a positive here, and then we have dB since the J's go away. And now we do our other side, draw a little parentheses here, our right-hand fraction, similar thing, CS plus CA, and now that is plus CBJ. And then we have the DJ term. So DJ is negative DJS. So that should be a negative. I won't draw parentheses since we have some negatives here. Negative DJS. Negative DJA. That's me. And we have DJ and BJ once again. So it becomes plus DB. So let's see where these cancel out here. Also the bottom, we can do it too. So we have S squared plus SA, that's minus SBJ, as well as, what else am I missing? A squared. So AS is already accounted for. Did I do it? S squared, SA. I think there's actually two SA. Minus SBJ, so then we have A squared, and then minus, so BJ times BJ, that's a negative with J squared, so it becomes positive B squared. Do that correctly, and then it's a plus SBJ, which I forgot. Okay, now we do some canceling out here, different color, so we have, let's just rewrite this, we have 2CS at the top, so that's taken care of. We have 2CA, so combining and canceling, we have minus CBJ plus CBJ, DJS minus DGS, ADJ and TJA, same thing, also canceled, and then 2 dB. Cool. For the bottom, we have S squared, and only this gets canceled out, so SBJ and SBJ. So S squared plus 2SA plus a squared plus b squared. So now we can actually end it here. So this is for if, I don't know, if a is not 0, maybe. And remember, we can relate this to, this would be for any complex root, but this is for how imaginary numbers get canceled out when you're combining those conjugate pairs. And for our case, we saw this with the CS plus D term at the very end of our transfer function, partial fraction decomposition multiplied by the sinusoidal input. So remember that was, where was that? Right about here. So it shows up there and also shows up here. So we were wondering, I kind of just didn't explain how that happened. That's what we're showing. So we want it to look like that. And the reason, or for how it gets to that, well, we do another simplification now. We're saying that a is 0. If we want this to get there, we say a is equal to 0. Then we get simplified further into 2cs plus 2db. And essentially these terms go to 0 there in the middle. You have s squared plus a squared plus b squared. So now we relate these to our transfer function. Well, I don't know what you want to call this. The phase shifted partial fraction decomposition, maybe. So we relate that. So we have c is equal to 2 small c, and that gives us our big C here. And then we have our D. I'm just trying to relate these two, I don't know, ratios, or, well, I guess technically partial fraction expansions. And now D is equal to 2dB. And S squared is actually just as is, remains the same. But this omega squared takes over the A squared plus B squared. So if I sub those directly in, you'll notice that this is C, this is D, and then this is omega squared. So that's how we get this general form here. Kind of just a substitution at the very end, if you ask me, but that's how it is. And then in the actual algebraic expansion, or I guess distribution, those j's cancel out. That's how the imaginary portion disappears. So that's why they exist here as pairs. So I think that was a little bit of part 1. Now we're doing the second part of part 1 here. So deriving how those non-repeating pairs yield a time domain response. So this is, well, this is actually, now we're talking about this open loop transfer function expansion, or I guess partial fraction expansion. We're going to show how these pairs of, well, expanded portions, and remember these aren't just real complex roots, there's also real roots in there. So, but we'll use them assuming they are complex roots. So since it's already in the partial fraction decomposition, all we have to do is take the inverse Laplace and apply some, I don't know, tricks like algebraic manipulations and identities to show that it yields that sinusoidal response with a phase shift. So now we'll start with pretty similar to what we did earlier. So I think C minus dj maybe, or I guess plus, and then S plus a plus bj. So is this the exact same what I did earlier? Yeah. So I'm using capital letters now, so that it looks familiar, I guess, when I do some of these substitutions. So C minus dj and S. Again, these are the complex residues and poles of the that closed loop that what did they call it here? I'm blanking on the name. Non-repeating pairs of the partial fraction terms. So again, technically the closed loop response, or I keep saying closed loop, open loop response. So now we apply our well, I don't know if this is an identity, it's just a Laplace transform. I showed it earlier where it was we have any coefficient e to negative bt. The Laplace of that is a1 over s plus b. So we apply that right here, even though it doesn't look exactly the same. Again, our residues are complex numbers, so there's two terms there, but we can treat it like a coefficient A1. So applying that down here, what do we have? Oh, what's up? So we have C plus dj, and that's our coefficient brought down. And then we have exponential A plus negative A plus bj t. And then we're adding that. So this can appear for all the terms, but we're focusing on the conjugate pair here. So this is what I guess each pair boils down to, that sinusoidal input function. So same thing, just C minus dj. And we have exponential negative and then A minus bj e. So if you notice here, I'm gonna put this in bigger brackets. You notice this term, this exponential, can actually be broken down as e to the negative at times e to the negative bjt. So both of these terms can be broken out that way, and we can factor out this e to the negative at, and I'll do exactly that. So we have e to the negative at, and then we can also do our, I can write it out, sure, why not? So I'll do this step first. I'll rewrite it. So e, this would be negative bjt plus, same thing, c minus dj, copy that down, exponential, and this would be positive bjt. Now we can group like terms here. So c plus dj and c minus dj. So rewriting once more, we have c factored out, and this is e to negative bjt plus e to the positive bjt. Then we have dj, so I'll do a plus dj. I don't know why I changed it to lowercase. I'll put it back. It should be all uppercase. Sorry about that. So these are all uppercase. I'm a little lazy. So so dj, and we want to do plus and minus, so dj e to negative b1j. I don't know why I said, is it b1? No, it's just b, right? Yeah, I don't know what I'm thinking. So that's bjt minus, and then the positive bjt. So if you remember, we've actually seen this before, this expression of exponentials of imaginary numbers. This is actually Euler's identity or Euler's number, where we said something along the lines of e to the imaginary number, maybe, and then times time was equal to this identity of cosine e. It was plus j sine e. And of course, if there's a negative there, you have to have a negative in front of our sign. So if we apply that to both of these, so I'll do something like 1 and 2. So applying that identity for 1, we have, so this is negative bjt, so we have cosine t, I guess bt, sorry, minus j sine bt. And then for that second exponential, we're adding it. And we have the positive version, so cosine bt plus j sine t bt. And these cancel out, and this cosine survives, so we have 2 cosine bt. And for the second, hopefully you see where this is going. The negative in front again, so cosine bt minus j sine bt. Recording, okay. And then now minus cosine, the positive, cosine bt plus, it's positive, right? Yeah, plus j sine bt. So now this time the cosine dies out, and we have 2 negatives, so that's negative 2, negative 2j sine bt. I do that correctly? Okay. I'll rewrite it so then you can see the next step pretty explicitly here. So we have c, and then this was 2 cosine bt. I don't know why I wrote the parentheses this time. dj, and then we had negative 2j sine bt. I'm probably going to remove those parentheses. So you'll notice we have 2j's again, j squared is equal to -1. So this negative gets canceled out. Then also, I'll just slip in a second step here. We have factor of 2 that we can take out. So I'll do both those steps here. So we have 2e negative at factored out, and then we have c cosine bt plus, since this negative canceled out with the j squared, we have d and then sine bt. Now you'll notice c and d, these can technically be any numbers, but what we're interested in is getting that phase. So if you remember, last time we did something along the lines of c, well, it's related to that phase shift. So it was, I think we use a sine phase shift, and then d was a cosine of a phase shift. So now we plug those in, you'll see that it resembles the, well, let me plug it in first. 2e negative at, just to be extremely explicit here. So I'll factor out this a. So that's a, and then we have sine phi times cosine bt plus cosine phi sine bt. And this is actually a trig identity that we've seen. So this is actually sine of a plus b is equal to exactly what we have up here. So it was sine, doesn't really matter which, right? So sine a times cosine b plus sine b cosine a. So I don't know why that became a sib, but sure, cosine a. So these a and b's represent our b and our phi's. And well, b, normally we use that frequency, omega. So doing that substitution, get 2e, I'll bring out that amplitude. So I don't know, 2ae negative at exponential. You'll notice that this a term, the real portion of this complex root, is what's controlling this sinusoidal input, or I guess response in our controller. So this is sine, we have phase shift plus b. I believe that is exactly what our problem statement is asking right there. So we just derived that. And remember that came from our conjugate pair terms, in which we took the inverse Laplace and then applied some substitutions with identities to simplify it down to our, I guess, time response in our transfer function. And notice that, again, I mentioned this a here is what's controlling this overall input, since it's determining whether or not this amplitude will decay or grow. So in the case where a is, I don't know, greater than 0, this is actually the bad point. So we'll have an amplitude that increases, and as it increases with time, you'll see that our function here will blow up, keep increasing. So that's amplitude will just keep increasing with our sine, versus the other scenario where we have a is less than 0, so it's negative. With a negative number, we have an amplitude. So we'll look at here. If a is negative, or did I do that incorrectly? Yeah, I did that backwards. I'm sorry. So if a is negative, it becomes a growth, right? Did I say that right? So a is negative, 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 positive, right? So if a is negative, I don't know if I said that right. And then if a is greater than 0, it will be, well, it's good since it will decay. Did I apply that correctly? I'm doubting myself now. A1, negative A. Yeah, we're good. Okay. Yeah, I don't know why I'm doubting myself. So the real portion, again, A is representing the real portion of the complex number. And if A is what's controlling whether or not our this sinusoidal response will keep increasing until it explodes to infinity, or here, where if it's positive, it remains a decaying response. So we got envelopes, and if phase is 0, so I should have mentioned that for both of them since we're starting at 0. At least it looks like I was. And then we have our sinusoidal function that eventually dies out. And of course, this amplitude is 2a, negative 2a, to show what's in front here. So that amplitude is what's controlling it. And of course, you might ask, what if a is 0? Then you'll have a constant time, constant sinusoidal function that will just remain the same amplitude of 2a. Yeah, so that's the derive, I guess, I don't know, response, time domain response is what they call it here. So so that was complex roots, and kind of going back to what I mentioned earlier, this stuff about poles. So remember the coefficients up top were residues, and I know in this case the variable name is a, so not to be confused with the real portion of the complex number of the root or pole in the denominator of this partial fraction expansion. Remember, we have our polynomials. There's one in the numerator and one in the denominator for our transfer function, and this was open loop. So after we did partial fraction decomposition, we took the roots of this polynomial in the denominator, and since they were real coefficients, we assumed the b's here were all real coefficients. With that being the case, it doesn't look like it's updating. That's not good. Oh. I'm gonna, oh, here we go. We're back. I was about to say it's pause, but that's pretty bad lag. But anyway, if those b terms were real coefficients, then we had the partial fraction decompositions where of residues and roots or poles that could be real roots or that could be complex roots. In which case, if they exist as complex roots, they exist as complex conjugate pairs. And you saw how the imaginary portion of those pairs dies out. And we also related that back to our CS plus D, the Laplace version of our phase shift, or I guess sinusoidal input. So yeah, that was the complex roots. And then here we also showed how they turned into a response of the sine phase shift, and the real portion, I guess the real number portion of the roots is what dictates whether or not this was increasing or decreasing and exploding to infinity or dying out. And you can actually see that here in our collab. I think this is maybe the last time here from the last video. The, I guess, relics of the exponential dying out. So we had an initial response and then it went to steady state. So those are the relics of that temporary change before we hit steady state from the in our case the open loop transfer function partial fraction decomposition. So remember the inverse Laplace was the exponential decay, so that's why it dies out. And going back to our residues here, talking about the poles and the down here, residues being coefficients and p being the poles. So going back to our OneNote, I feel like I'm kind of repeating myself here. But you know, it doesn't hurt to be explicit. We talked about real and complex roots. So with the I kind of showed our, I don't know, notation for b and p. So b was the roots. We showed this, I think I used this notation in the last video as well, but normally they're written this way with the poles. And in which case with real roots, I think now we're getting to the, wow, that's really bad lag. I circled this. Okay, the A1 with the pole notation in pink there. So I think now we're getting to the second part here with real and complex. So if we have our expansion of that transfer function, A1 S plus B1, and remember this is also the same thing as A1 S minus P1. So we're assuming the coefficients were real, and the roots are if B1 and P1 are real roots, I should say. Then we have the inverse Laplace being A1 e to the negative B1t and A1 to the P1t. So of course, the signs matter. If you're doing it in notation for B1, B1 needs to be positive for this to remain in decay, which is what we want. And for using poles, we would want the P1 to be negative here. I mean, technically, this is a double negative, so it becomes positive. So you want the P1 to be positive. Am I doing that right? Sorry, negative. Negative, so it is an exponential decay. So a negative, negative, 3 negatives makes a negative. So I'm just going to write it as a positive for my sake. So remember, exponential decay. Hopefully this isn't going too overboard in detail. Decay would die out. That's what we want. This is good. Equals decay, so we're not exploding our function. So again, we want exponential decay. And for if this wasn't the case, then obviously the other case would be if B1, why? Hopefully I don't need to draw this, but if B1 equals negative, then you have growth, and P1 is positive, you also have exponential. I don't know, I'll do X. So this is what you would get. Again, just plugging it back from our two inverse Laplace transforms. And obviously the growth is not good since that makes our function go crazy. So kind of looking on this in the complex plane, there's this idea of left-hand poles and right-hand poles. Honestly, it's just, I don't know, perspective from 0. So we look at it from the pole side, not with the B. So I can draw this out here. We have the complex plane where x-axis was real numbers, and then the y-axis was imaginary numbers. So we want to be on the left-hand side for the left-hand poles. So this is our real number, and then they exist as pairs. So maybe we had something like a plus bj and a minus bj. And remember, this a is the exact same a that appeared in our that controlled that time response in our controller, or in our I guess feedback loop, and whether or not it was positive or negative determined if it was decaying or not. So no, what am I doing? It should be right, negative AT. Am I sure that's right? Because it should be negative, unless I'm. All right, let me pause here and get my thoughts sorted. Sorry about that. Yeah, I don't know what I'm thinking. I'm correct. I'm just overthinking things. I was trying to think that if they should match the A and the poles, but it's just simply how we're writing it, which is they're equivalent. So in our case, we had A minus BJ in a complex number format. So A plus BJ, A minus BJ, if this would like to update. Right there in the red brackets, or I guess in the blue here, that was our the partial fraction decomposition, and then with complex numbers for the residues and for the roots, technically poles as well. So if the real portions of that root or pole, the a value, if that was negative, it would, yeah, if it was negative, it was exponential growth, which is bad. We don't want that. versus exponential decay if a was positive. So this a, the real portion of the root, is what's causing it to decay or grow. And the same thing goes for here. I see where I was trying to mistake it. So this a is actually negative, since you notice that the a is the real portion, and then bj's are the imaginary. So a is on the left-hand side of 0. So that's why it is correct in saying negative for the left-hand pole. Yeah, and our left-hand poles exist again on the left side of 0. And for the right-hand side, they also exist as pairs, but obviously we don't want this to appear. Now, the important thing is this cusp of stability near 0, kind of similar to the amplitude ratio, in which case you don't want to be near that amplitude of 1, since remember, it would self-magnify if you were over 1. A similar case here, but different concept. There's also a sinusoidal input, but what we're worried about is that, again, that amplitude. So if that amplitude is not dying out as relative to A, if A is not a negative enough, then it will kind of, well, again, I mentioned on 0, the value of that amplitude remains constant, since remember, this A is controlling that decay. So if A equals 0, then it becomes just 1. Oh, what am I doing? E to the 0, which is 1. So you'd have that constant amplitude, a constant sinusoidal input or time response in your system, which can be good or bad depending on the system, but that's what happens. So left hand pole, right hand pole. Left hand pole is what we want. Right hand pole is what we don't want. So again, the poles, if the real portion of the complex roots, if they exist as complex roots, if it is negative, then we have a decay, which is what we want. And if it's a real root, we also want it to be negative. So did that delay? Wow, that was like 3 seconds. Okay. So is that all? Purely real versus complex and negative, positive, real parts. Yep, we did just that. And we even drew it on the complex plane. So just to wrap up, quick summary. Took a look at our closed loop, or open loop transfer function. How we had a different notation. We went from s plus b1 to s minus p1. Those are the same. It's just a matter of signs. We did an example where we solved the partial fraction decomposition computationally using SciPy signal residue. I took an A and B array where the denominator had a higher power, in our case, written right there, and it gave us thankfully a good example of a complex number where they exist as pairs where the signs were flipped, and then we showed that they existed as pairs because the coefficients in the denominator of our transfer function, right here, these coefficients, those b's, were real. So if they were real, then our complex roots, while they could exist as complex roots in the residues or the poles or the roots, same thing, while they can exist as complex numbers, they have to exist as pairs of conjugate pairs. And that way, doing the algebra, we saw that the imaginary portions canceled out. And we also related it back to our CS plus D, this sign, I don't know, partial fraction decomposition that was related to our phase from the previous problem. I feel like I've said this like 3 times. But anyway, we also derived the expression for that sinusoidal input with a phase shift, doing the inverse Laplace and some identity substitutions to simplify it down further. I think we did trig sub and a Euler's, not trig sub, but a trig identity and a Euler's number substitution to simplify it, and we found we got the exact same. Well, we had to prove that it became that sinusoidal input with a phase shift, and we saw that the real number portion of the roots, this a value, controlled whether or not the amplitude, this 2a, would exponentially increase and explode our system or decay and die out, just like we saw in the collab earlier. And then for real roots, we quickly discussed why um, the signs matter. So we talked about left-hand poles and right-hand poles. Left-hand poles is what we want, where the poles are negative. They're on the left-hand side of 0, and right-hand poles to the right of 0, which we don't want. And we saw how we want to achieve that exponential decay with the left-hand poles versus the right-hand poles having an exponential growth. Okay, so pardon the over-explanation, but I think we're done here. So yeah, thanks for watching.